Welcome to Bitcoin Cash University. In this episode, we're going to go over CashScript, what it is, and can you get into it. So even if you've never coded before, that's actually where I began, is I didn't really have any coding knowledge when I first got into blockchain coding. So CashScript is the second language I learned, the first one being Solidity for EVM, so Ethereum style networks. And after learning that and doing a project, I actually moved over to UTXO and CashScript on Bitcoin Cash. So if you've learned Solidity and you're doing EVM coding, CashScript is essentially that, but for the Bitcoin Cash network, and it's using a UTXO model instead of the EVM model. So they're quite a bit different, but the core results of being able to do smart contracts on the chain are the same. If you've never done coding before, that's essentially what CashScript is that you're doing smart contracts on Bitcoin Cash itself. So this is the cashscript.org website. You will definitely want to come here and check out all the information and tutorials. You'll probably be referencing it quite a bit just to check out all of the stuff it has. So like these, for example, are some of the commands you can use in it, what they do, examples is laid out quite well. There are also example contracts in here. We will go over one of these as well in a moment, but this is one place to find some. Basically, if you're interested, this is probably one of the main go-to places to start that adventure. On the cashscript.org website, you can also find this list. So they have some example contracts on it that I just showed you. They're in this list on this GitHub. So this is the CashScript GitHub directly under their examples. There's actually some other examples on here. So we're actually going to look at this transfer with timeout right here. So this is that transfer with timeout contract. That's the whole thing in its entirety. This is what CashScript looks like at a basic level. If you've done Solidity, this will look vaguely familiar. So it starts with a pragma up here. So this is just pragma CashScript. It always looks like this. This is saying what version of CashScript this contract has been created with. So, and it's using semantic versioning. So this little caret symbol is saying that it can use any version of CashScript within version 10. So it could be 10.1, 10.2, etc., but not 11. And just to show this process, if you weren't sure about this pragma thing, you could just go to the CashScript website, look up pragma, and it'll tell you exactly what it is. So the purpose of this contract is that you want to send money to somebody's address, but you want them to actually claim it. You don't just want to blindly send it. You want them to initiate taking the money. So at a high level, it's you're going to create this contract, you're going to put some money into this contract, and you're going to tell the person, the recipient, that they can take the money out, but they have to claim it. But if they don't claim it within a certain amount of time, then they forfeit it, and the sender is allowed to take the money back. So within these two round brackets, we have three parameters that we're creating the contract with. So we're giving a public key, which belongs to the sender. So just think of this as the address of the sender. And we're giving a public key of the recipient, which again, just think of it as the address for the recipient. We're giving an integer, which is a timeout. And this is a number. We're saying basically how long does the recipient have before the sender is allowed to reclaim the funds. So this sets up the contract and the parameters for it. So the contract can be interacted with in two ways in this case, because it's got two functions, transfer and timeout. So transfer, so when we initially create the contract, the sender has to actually put some coins into it, some BCH into it. So transfer is taking those BCH and allowing the recipients to take them out. So the way to think of CashScript contracts, and this will be a little bit different than Solidity as well, for those EVM coders out there. This function is basically just a checklist, and this checklist has to pass to allow the money to come out. So the only checklist, the only task we have on our checklist is this one require. So this thing must be true. And if this thing is true, then anything else is allowed to happen. So in our case, we could make a transaction that is taking all the money out of this entire contract using the transfer function because there's no limits on anything about Satoshi amounts or anything like that. The only limit we're putting on the entire transaction is that this require needs to be true. So what is this require doing? So it is doing a check sig. So this is a check signature. And check signature needs two parameters. It needs a signature and it needs a recipient address, so a public pub key in this case. So as we said, the pub key is basically the address of the recipient, the person you want to give it to. And when you call the function contract, you have to give it a signature. So what checksig is doing is checking that is the signature that is being provided to it, which is this recipient sig that's being given to the transfer function, does it belong to this recipient address? And the way public-private keys work is that only the owner of this address can provide a signature for it. Nobody else can. So you're essentially proving that whoever runs this transfer function is the recipient, whoever controls this address. So only the recipient is allowed to take the money out. So to just quickly go over again, the sender puts money into this contract. Anybody can call the transfer function, but you have to give it a signature. And the check signature is checking, is this signature that the function is being given for the recipient address? And the only person that should have that signature is the person that controls this recipient's public key. So the next function is timeout. So this is what we're using to put a time limit on the recipient. So again, we are calling it timeout. It needs a parameter, which we're calling the sender signature. So same thing we're doing with transfer, except this time the signature being provided is from the sender. So we're essentially proving that the sender, whoever controls this public key, is the one that's calling timeout. And we do the exact same thing. So we have a require, we're checking the signature, doing exactly that. Is this signature being given to the function belong to the sender? If it does, true, this passes, it goes to the next. So we go to our next require. We are saying, is the transaction time greater than or equal to the timeout? So the timeout is something the contract was created with at the very beginning. So it's an integer number and it'll just be some number. Transaction time is called an absolute time lock. So this is basically the block height that happens on the blockchain. So as new blocks come out and are generated by the miners, they get added to the blockchain on top of each other. So this is just a block explorer for Bitcoin Cash. So we can see at current time of recording, this is the block height we're at, 896,837. So that is the current transaction time. So if we come back to our contract, if we set the timeout to 897,000, which is a little bit higher than what it currently is, then this is going to fail because the current transaction time on the blockchain that the miners are operating on is not bigger than 897,000. So this timeout, if you tried to call it even with the proper signature for the sender, this require will fail. Once the miners get up to 897,000 blocks, then this timeout will pass and then the sender will be allowed to call the timeout function and reclaim the funds. So this is just a very simple example of how it's basically you're going down a checklist. You're putting constrictions on the transactions that can be created. Only the sender can do the timeout function. It has to be over a certain block time. And this can be changed a ton. So just as an example, instead of transaction time, so this is setting a absolute time lock into the future at some point. You're selecting a block number saying it can't happen until then. We could change this to transaction.age. So this means how old the UTXO is. So in this case, we create a contract. So exact same contract. We put money, so the sender puts money onto the contract, like just transfers it to the contract. Once you do that, that's a UTXO living on top of this contract inside of it. And that UTXO will have an age. The age is how many confirmations it has existed for and been confirmed by the blockchain. So when you first send it, it'll have 0 confirmations. If you give it an hour on average, because blocks are 10 minutes on Bitcoin Cash, you'll have 6 confirmations. So its age would be 6. So using transaction age in the timeout, this timeout now becomes a relative time lock. So if we said timeout was going to be 1,000, then this line now changes to funding the contract with BCH creates a UTXO, and that UTXO has to be at least 1,000 confirmations in order for the sender to reclaim the funds. So just kind of 2 ways to do timeouts. You could also just expand these out quite a bit. So we could put this line here under the transfer. So this is sending the funds to the recipient. So this .active input index is equal to 0. So this has to do with the ordering of the UTXOs inside of the transaction when it gets built. So the very messy way I'll show this. So imagine you have a contract, and we'll depict that contract by this extremely amazing looking ice rink. And on this ice rink, there are players that are skating around. And in this case, these are the UTXOs inside of the contract. So if you're building a transaction over here, it'll have inputs and outputs on it. And you might have your wallet down here, and this has your UTXOs inside of it. And you're going to take one of them and put it inside the transaction. But you're also going to interact with this contract and use one of its UTXOs, and it's also going to go inside your transaction. So you're taking one of the players from the ice rink. In order to take that player, you have to call one of these functions on the contract. There's no way around it. You have to use one of them. So because you're interacting with the contract, you can define the rules that the transaction will have to follow. And that's why this check signature works, because you're required to provide this parameter and it's required to be true. So if we added this active input index is equal to 0, what we're saying is that if you're interacting with this contract, if you're pulling that player out, well, when we verify the UTXO's logic from that contract, that player needs to be input 0. You're not allowed to build this transaction over here and have the player be input 1 or input 2 or input 3. It has to be input 0. And doing this allows us to open up a lot of new functionality that's probably not clear yet, but will become over time. So for example, if we added this next line here, what is this doing? So we're saying we're requiring the player, the UTXO from the contract, to be input 0. So that allows us to then manipulate the inputs and outputs a little bit more. So we're saying the output 0 locking bytecode must equal the input 0 locking bytecode. So the locking bytecode you can just think of as the address. So input 0 we have locked down, saying it has to come from the contract. So that's basically the contract's address. But we're saying now that output 0 also has to go to the same blocking bytecode. So essentially we're pulling one UTXO from the contract, but we're also saying that the first output, which is output 0, also has to be going to the contract. So this kind of breaks the transfer function a little bit for what we intended, because now we're having to send something back to the contract. So what else could we do? We could add this line. So this is another require, saying that the output 0 value must equal the input 0 value. So to run through again, we are grabbing a UTXO from the contract, which is input 0 over here, and we're saying that it has to, output 0 also has to go to that same address. And then we're saying output 0 also has to have a value. So this is the number of Satoshis on the UTXO. In other words, the amount of BCH. And we're saying that this output 0 that we're going to create has to have Satoshis equal to the inputs 0. So if we look at our little paint thing again, so we're saying that this UTXO that's coming out of the contract is going into the transaction, but the transaction has to create an output that also goes back into the contract with the same value. So that doesn't work, you probably think. Why would we do that if we're trying to send money to somebody else? The answer is you're right, it doesn't work. So what we could do instead is to say something like it needs to be equal to the input value minus 1,000 Satoshis. So what is this going to do? Well, if we look at our paint again, if we're pulling this UTXO out, this UTXO might have 5,000 Satoshis on it, say. And this contract specifies that if the transaction is going to interact with it, it needs to send a UTXO back to the contract with 1,000 less Satoshis is what it started with. So it'll have 4,000. So what does this do? This makes it so that you're now pulling 1,000 Satoshis off of that UTXO on the contract instead of the full amount. So we put a restriction on the value. You're only allowed to take out a certain amount at a time. So is this useful in any way? It could definitely be useful in some ways if you designed it a little bit better, because this transfer function is still extremely broken. Because if you're trying to restrict some value transfer, like slow dripping it to somebody, this contract doesn't really do that, because all it does is allow 1,000 Satoshis to be taken off the UTXO at a time. But the person can just keep calling this function over and over and over again. There's no limits on it. If you wanted to put limits on it, you could probably design something using a time lock like this one does. So maybe this transfer function can only be called every certain amount of blocks. And there's other contracts in the examples on the CashScript that go over that. So if we just go back to the CashScript examples, there's a bunch of other contracts here. These Makinas ones have some time locking stuff in them you can look into, as well as the HODL vaults cache. So that's a very basic CashScript contract that we went over that I started playing with and adding things into. I'll just show the documentation I've been doing on my own contracts, and I'm not saying that this is good or the proper way you should do it. But especially if you're going to watch the rest of these videos, you'll probably see a bunch of these, so I may as well go over it. So I just put these comments in above each of the function. This top is basically describing what it's trying to do. And that comment was for when it existed like this, technically. So in this case, on this original transfer function, when the only thing we're doing is checking the signature and that's it, we have no other checks in the function. So the contract isn't requiring anything else. So in my comments, I put the inputs that are going to be in the transaction and the outputs that are going to be in the transaction. In this case, the contract doesn't have anything else. This transaction that we're building and pulling one of these UTXOs from the contract, it could have, 100 inputs and 100 outputs. This function doesn't care because it's not checking any of that. It's only checking this check signature. So in this case, I just, put any number of inputs, any number of outputs. And since we're pulling from the contract, at least this contract has to be coming from the contract, and the outputs can go anywhere because, again, we're not restricting them at all. However, if we did add those lines back in where we're restricting the inputs and the output for number 0, this is how the comments would update. So we would require for this function transfer that input 0 is the contract UTXO coming from the contract. And we're doing that because of this active input index equals 0 right here. And then for the outputs, we are also requiring that there is a contract UTXO being sent back to the contract. And that is from these two lines here. So we're specifying output 0 for the transaction. Its locking bytecode must equal the input 0 locking bytecode. So this is saying that it's coming from the contract in input 0 because we've locked it down. And we're using a UTXO on this contract. And the output 0 must be going to the same bytecode. So we're saying basically the same contract. So just to give another example, this is one of the functions from the Badgers contract, which is the badgers.cash website app. And in this case, we have one input, which is a lock UTXO, which is required to be an NFT, which we haven't gone over yet. And then on the outputs, we have 3. So one is a NFT, one is BCH only, and one is a fungible token, which we also haven't gone over yet. And then this is kind of what like an active live in production contract looks like. So might be a little overwhelming. There's some stuff we haven't gone over, obviously. But if you look at it, we can see here, these outputs are all 0. So these requires are all manipulating the output zeros in some way. So we can see, you know, value, so it's setting 1,000 Satoshis. Token amounts, well, it's pretty obvious it has to do with tokens. So must be a token on this output 0, and we're setting it to the input 0. So kind of the exact same thing we were doing before. We're saying that the output has to equal the input. So we're kind of transferring this token amount from the input to the output on the transaction. And same thing, outputs 1, manipulating it, and outputs 2, manipulating it. So you won't understand a lot of these specific things like NFT commitments and stuff like that, or how it's doing splits, but you can see the general structure, and there's definitely a logic to it that you can follow through. And things are very self-explanatory with CashScript as well, because if we look at this, for example, you can probably guess what these two commands are doing just based off what I've told you so far. For the transaction, we're limiting the inputs length to 1. And if we look up here, I've specified there can only be 1. And that's what this line is doing. So if you tried to add another input into this, it will fail because this line will be no. And same thing with outputs. We limit it to 3, so the double equals are saying it must be that. So I'll just give a quick rundown. So this Badger contract, this is a live in production one, and I'll show you the website in a second. But it's only one contract. So it is this function lock. So this lets you lock up BCH into the contract. There's a function unlock to take the BCH back out, and this also gives you some of the Badger tokens for doing that. And then there's a function withdraw. And this is just one for myself as the admin to change a value on the contract. So this one doesn't even get interacted with by anybody. So it's basically just 2 functions, lock and unlock, and that's it. And the result of that contract is that you can create apps like this. So this is live on BCH right now. We can see there's 79 locks sitting on the contract, which is 155 worth of BCH on them. And so you just go into here, set how much BCH you want to lock, how many blocks you want to lock for, and based off the logic of the contract, it specifies how much BCH you'll earn, how long it'll be locked for, and we can see 4.3 million BCH has been, or not BCH, Badger coins have been provided to people for locking so far. And we can see 11 BCH floating along here that needs to be unlocked. So we'll just do that. And so this is querying the building a transaction, and the contracts are going to do their stuff and check it, and it succeeds. So I hope this was useful. A very, very quick overview of CashScript. There's a bunch of other topics we will be going over, like tokens and NFTs and things like that. But I hope this shows you that it isn't that hard to get into. It does make sense. And I myself didn't start with a coding background, and I kind of jumped into this feet first. And I hope this gave you a little bit of confidence to jump in yourself. And that's it.